The process initial condition, let's pretend it's hidden unless given initial condition. If you did not have the solution curve and you just had the point generated from Euler's method, you still get a rough idea of what the solution curve would look like. But this curve is not the same as the solution curve, as some approximation errors involved. This was the initial condition point. I wrote x0 and y sub 0. Our goal is to find some points further down the line that are close to the solution. So ideally, I would find points like here and here. This is based on tangent lines. x0 plus that predefined fixed distance in an equal interval is called stress size h. The new x coordinate x1 equals to x0 plus h. Then talk about how high is y1. So basically, it's the height at y from here to here. So let's look at these three sides of the right triangle. Can you see the length of the base has the length h sides? The differential equation of dy divided by dx equals fxy is the slope at any given point. Give you the slope of the pink line of the point x0, y0 on the curve. The slope of the tangent line equals to the unknown extra height divided by h to the unknown extra height divided by h. The unknown height is hf of x0, y0 equals to y0 plus extra height of h multiply f of x0, y0. The same way to find the next coordinate x2, y2 for the most updated slope of point. The final step we find xn equals yn minus 1 is the previous guy plus stress size, and yn equals to is previous y value plus the extra height, that's the stress size, multiplied by f of xn minus 1, yn minus 1, and this is Euler's method. It generates a table of points that are close to the solution curve that's constantly updating. I will admit the error starts to grow over time, but it's slower and stays a fairly good approximation. Now let's solve the IVP using Euler's method in Microsoft Excel. In column we'll have our xn values, in column B our yn values, and in column C the function fxy yn is equal to x divided by y power 2. First enter the initial x value 0 in cell A2 and the initial y value 1 in cell B2. We add the stress size h to the previous x value in cell A3. Enter A2 plus 0.1, drag down to fill the column. Next in cell B3, enter the formula B2 plus 0.1 multiply A2 divided by B2 power 2. Drag this formula down to fill the column. In column C, we'll compute of fx and y in cell C2. Enter the A2 divided by B2 power 2 and drag it down. When x is equal to 1, the approximate value of y is equal to 1.393. To find the exact solution, the separate variable and y power 2 dy is equal to x dx. So integrate y power 3 divided by 3 is equal to x power 2 divided by 2 plus c multiply 3 of both sides to get y power 3 formula is equal to 3 multiply x power 2 divided by 2 plus 3c. From y0 is equal to 1 sub x0 y0 into y power 3. 1.3 is equal to 0 plus 3c. C is equal to 1 divided by 3 sub c into y power 3. Y power 3 is equal to 3 divided by 2 multiply x power 2 plus 1. So y is equal to the cube root of 3 multiply x power 2 divided by 2 plus 1. Sub x0 into y to find the exact value of y1. Y1 is equal to the cube root of 5 half. It's equal to 1.3572. We know the approximate value of y1 from Excel Euler's method. Y1 is equal to 1.3393. Then calculate approximate error is equal to exact value minus approximate value is equal to 1.3572 minus 1.3393 is equal to 0.017.